So, we are in this course we are going to learn graph theory. For this course I will be using the following books. One is a graph theory by Reinhard Diestel, another one Introduction to Graph Theory by Douglas West, and the Graph Theory by Bondi and Murthy, and Bolabash Modern Graph Theory. So, there are many other books in graph theory. So, you can use those books also if you like, but most of the time I will be taking material from these books. To begin with, let us consider the question, what is a graph? We say it is a triple, the vertex set V of g, the edge set E of g, and a relation which associates to each edge two vertices. These two vertices are called the endpoints of the edge. To an edge we associate two vertices which are called the endpoints of its edge. So, it is much easier to represent a graph by a drawing. So, it can be like this. Let us say I am drawing these vertex sets. This is 1, 2, 3, 4, 5. So, 1, 2, 3, 5, 4, 4, 5 are the set of vertices, and the edges can be say E1, E2, E3, E4, E5 say. So, here the edge E1 is associated with the two vertices 1 and 5. It is called the endpoints of this edge E1. The edge E2 is associated with the 5 and 2, the endpoints of E2, like that. Now, what kind of edges are possible? So, it is not necessary that the two vertices associated with an edge, the endpoints are distinct vertices. For instance, it can be like this, the two vertices associated with this edge say E6 is 2 and 2. So, it is called a loop because both the endpoints are same. Now, it is also possible that there are many edges which are associated to the same pair of vertices. For instance, it is possible to have several edges say E2, say E7, E8 such that the two vertices associated with them are the same 5 and 2. So, then we call this some multiple edges here between these two vertices. When we do not have any loop or multiple edge in a graph, then we say that that graph is a simple graph. It is also possible that our vertex set is infinite, the edge set is infinite. But if we assume that both the vertex set and the edge set is finite, then we say that it is a finite graph. Usually in this course, most of the time we will be talking about finite graphs and simple graphs. If at all we are talking about non-simple graphs, we will be explicitly mentioning that, or if we talk about infinite graphs, we will be explicitly mentioning that. Now, let us consider some example graphs which are some simple graphs. The first one is complete graph. What is a complete graph? Where corresponding to each possible pair of vertices we have an edge. So, for instance, let us consider the simplest example. Let it be the vertex set be a singleton, just one, then there is no pair of vertices, then this itself is a complete graph, no edge, right. So, we are talking about simple graphs here, and then say suppose there are two vertices 1 and 2, then there is only one pair. So, this is a complete graph, this is called K2, complete graph on 2 vertices. So, suppose there are 3 vertices, then there are 3 pairs, one is like this is other, the third one is this is 1, 2, 3. This is the complete graph on 3 vertices. How will the complete graph on 4 vertices look like? So, I will draw 4 nodes 1, 2, 3, 4. So, I put all the possible edges. So, because there are 6 pairs here, I have to add all the 6. This is the complete graph on this thing. So, when I say complete graph on n vertices, there are n choose 2 pairs, say if V of g, the vertex set of G is called V of g. If this is equal to n, then n choose 2 pairs of vertices, right. Are possible. Corresponding to each pair, we have to have an edge, then it is called a complete graph on n vertices. The notation for the complete graph on n vertices is Kn. Now, the next thing is 2 notions, subgraphs and induced subgraph. So, given a graph G, we say that another graph H is a subgraph of it if the vertex set of H is a subset of the vertex set of G, that is what we mentioned. So, V of H is a subset of V of G, and the edge set of H is a subset of the edge set of G. The next statement is just to say that the edge set means we are not just naming, we are just using the same name, but the assignment of vertices to each edge is the same in G and H. For instance, rather than explaining like this, it is better to draw a graph and show. So, for instance, let us consider this simple example. So, this is called a cycle graph Cn. So, the cycle, this is called a cycle graph, the cycle on n vertices Cn. And say suppose we collect these vertices using red, let us say these vertices, and then take some of the edges here. So, this one, this one. So, here the vertex set, this red colored vertex now is a subset of the vertex set of the original graph Cn, and the edge set is also a subset of the original graph Cn. So, then this is this looks like this. This is a subgraph for the original graph. So, let us maybe you can consider a little more complicated, some little more complicated figure. So, let us say consider this graph. Now, if I consider this vertices, so and this edges, this is a subgraph. So, this black edges and these vertices form a subgraph of this big graph, and so and then the next is a notion called induced subgraph. What is an induced subgraph? So, the induced subgraph means if we select a few vertices, a subset of G, and then look at the edge set. For instance, we can consider our earlier example. So, this was here we selected the vertex set, and this is what we got is something like this, right. This is called a path graph, say. So, something like this is a path graph on 3 vertices, and see, when I consider these vertices, all the edges of Cn, the original graph, which have both endpoints in the selected collection of vertices, is there in this subgraph also. Then this is called an induced subgraph. So, in the next example, it is more clearer. Here I have selected this vertex, this vertex, this vertex, and this vertex, but the edges are only this, and this. This edge is not selected. So, this is not an induced subgraph. To make it an induced subgraph, you have to add this also. So, this is the induced subgraph. Now, the next one is a connected graph, the notion of a connected graph. We say that a graph is connected if each pair of vertices belong to a path. That means, suppose we can consider this simple graph. Okay. So, here there are 6 vertices in this graph. So, 1, 2, 3, 4, 5, 6. So, between 1 and 2 there is a path, between 4 and 6 there is a path, but suppose I consider the vertex 1 and the vertex 4, then I do not see any path. Path means if I start from here and then follow an edge, and then I cannot reach here. So, this is a disconnected graph. Now, how do I make, for instance, if this has to become a connected graph. So, for instance, I can put this edge here. So, then this becomes a connected graph. That means, if I start from any vertex, I can reach any other vertex using a path. A path is like this. So, this is the notion of the connected. In this lecture, I am not going to tell all the definitions as in a textbook, because that will be very boring for a class. So, what I will do is I will introduce the notions which are necessary to understand the things as and when it is required, but it is also advisable that the students can go through the introductory chapter of one of these textbooks which I mentioned earlier, say the ones which I mentioned earlier, for instance this one. So, this any of these 4 books, you can see the introductory chapter explaining many the commonly used definitions, words, the terminology, etc. So, one can read that, but otherwise anyway I will be explaining the terms which I use as and when it is required. Now, one word which we always use is isomorphism. This is, for instance, we sometimes say that there is a path on 5 vertices is a subgraph of G. It is essentially a path on 5 vertices is isomorphic to some subgraph of the given graph, like that. So, therefore, it is I will just mention this word. So, an isomorphism from a simple graph G to a simple graph H is a bijection such that whenever uv is an edge of G, then the corresponding pair f of u comma f of v is an edge of H. So, to understand this thing, we can take an example. So, here let us draw a graph. So, this is our G here 1, 2, 3, 4. So, now consider another graph like this. So, looks very different, but then we say that these 2 graphs are isomorphic, because let me name it like this A, B, C, D. because I can map vertex 1. So, the function f will map 1 to a. So, that is 1 will be mapped to a, 2 can be mapped to b, 3 can be mapped to c, and 4 can be mapped to d. This is the function f. So, as we want it, so whenever there is an edge, that means 1 4 is an edge. So, the corresponding vertices a and d, between a and d there is an edge. So, we say that for similarly 1 3 there is no edge. So, between a and c, the corresponding vertices here a and c, there is no edge here. So, therefore, we say that there is an isomorphic. These two graphs are isomorphic. Essentially, that means they are the same graphs, but maybe we have drawn it differently, something like that. So, we can take another example, for instance. So let us take this graph. Right, 1 2 3 4. So, another graph I can draw like this. Let this be G1, and then let me draw another graph. This is like this. So, at first look, these two seems to be very different graphs, but in fact this 1 can be mapped to this thing, say 1. So, this correspond to this, say 4 can be mapped to this one, say, and 3 can be mapped to this thing. In other words, this triangle comes here, and this 2 can be mapped to this. Sorry, 2 can be mapped to this. This 2 1 2 1 there is an edge, 2 3 2 3 there is an edge, 2 4 this edge you can see. So, you can see that whenever there is an edge between say I and j here, the corresponding edge is present here also. Otherwise, if there is no edge, then that edge will not be there. So, this is the notion of isomorphism. So, next let us say so we can consider a graph, and then if we can ask this question, is there a subgraph for G which is isomorphic to a cycle on 3 vertices, 4 vertices, 5 vertices. If there is no subgraph for G which is isomorphic to a cycle, then we say that it is an acyclic graph. So, a graph without any cycle, that means in it, an acyclic graph, is called a forest. So, how will a forest look like? So, it may look like, say, see there is no, we cannot put a cycle, right. This may look like this. So, this is a forest. Suppose it is a connected graph also. Here you see this is acyclic, but not connected. This is a disconnected graph. But if it is a connected graph also, then we say that it is a tree. So, for instance, what kind of edges I can put to make this graph connected? For instance, I can add, say, this edge and say this edge. So, now this has become a tree. Now, if I, for instance, if I add this edge, then what will happen is this cycle will form, then it will not be a tree, neither will it be a tree nor will it be a forest. So, I cannot put that. So, this is the notion of tree. The next notion I want is that of a bipartite graph. We say that a graph G is bipartite if its vertex set is the union of two disjoint, possibly empty independent sets called partite sets of G. So, a subset, so what do I mean by independent sets? if I consider a subset of a graph and look at the induced subgraph of it, and if you do not see any edge in it, then it is called an independent set of that graph. So, for instance, we can consider in this graph, for instance, we can consider this, say some of these vertices, say this one, this one, this one, this one. So, this 4 vertices. So, if I consider the induced subgraph on these 4 vertices, we will just get something like this, right. There will not be any edge in it, right. So, therefore, this will be an empty, sorry, this is an independent set. This is called an independent set of this tree. So, we say that a graph G is bipartite if we can partition the vertex set of G into 2 groups such that the each of this collection group is inducing an independent set in the graph. So, we can take some simple examples, like for instance, I can consider a cycle. So, is this a so let us say consider this cycle. This cycle. So, now how do I partition it into 2 collections such that each collection induces an independent set? For instance, I can say this I will put it in one part, this I will put it in the same part, and this also I will put in the same part, and the other one, say this and this I will put in the other part. So, this black vertices form induce an independent set in this graph. Similarly, this induces an independent set in this graph. So, every edge in this graph is going from a red vertex to the black vertex. So, for instance, you could have grouped. So, if I number it as 1, 2, 3, 4, 5, 6, I could have placed 1, 3 and 5 my black vertices on this side, and the red vertices, say 2, 4, sorry, 2, 4 and 6 on this side, and the edges will be 1, 2, 3, 4, 5, 6, 1. So, the edges are always going from one side to the other. So, this is one way of viewing the bipartite graph. Right. So, a graph is a bipartite graph if I do this thing, right, in a graph. So, is it possible that any graph is bipartite? So, let us consider some simple examples, like so consider a tree. So, this is a tree. Is this a bipartite graph, for instance? Simple. Yeah, this is a bipartite graph because we can place, say, this in one side, and then immediate children of that can be placed in the other side, right, in the other part, and then the children of this can be placed in the other part like this. So, for instance, if you want to see it in this 2-part form, so 1, 2, 3, 4, 5, then I can place 1 here, and then 2 and 3 should go to the other side, 2 and 3 should go to the other side, this 2 vertices, and 4 and 5, so the neighbors of 2 should come to this side, 4 and 5. So, you can see that, so by extending this argument, you can see that any tree can be placed like this on two sides. So, without any edge appearing in this side or without any edge appearing in this side, right. So, all the edges will go from one side to the other. The trees are like that, trees are bipartite graphs. Now, so we saw that some cycles are bipartite. Is it true that every cycle is a bipartite graph? So, we can consider this cycle, for instance, simplest cycle, the triangle 3, this is called a triangle. So, or 3 cycle C3. Is this a bipartite graph? So, suppose this is a bipartite graph, then we should be able to place the vertices in 2 groups in such a way that the edges go from one side to the other. So, let us say 1 is placed in this thing without loss of generality, this side. Now, if 1 is placed here, the 3 and 2 should be on the other side. 2 and 3 should be on the other side, because there is an edge between 1 and 3, 1 and 2. But then between 3 and 2 there is an edge, it has to come here. So, this will become a problem, right. So, this will be flop. So, therefore, this triangle cannot be a bipartite graph. So, what kind of cycles are not bipartite? So, with some thought we can see that every even cycle can be placed like this, but the odd cycles cannot be placed like this. So, we can try to place 1, 2, 3, 4, 5, 6, 7 vertex. So, this is the 7 vertex C7. Can this be placed like this? So, it is not possible. For instance, if I place it in the first part, and then I will have to place this and this in the other part, and if I then I will have to place this in the first part, and then I will have to place this in the red part. This also has to be in the red part, but there is an edge between these two red parts. So, therefore, this cannot be a bipartite graph. So, this is what a bipartite graph is. Now, we will and now see, because the triangle, the K3 is not a bipartite graph. So, we can we know that no complete graph Kn where n greater than or equal to 3 is a bipartite graph, because if the complete graph on 3 vertices itself cannot be placed like that, then a complete graph on more number of vertices cannot be placed like that. So, what about but then there is a notion of a complete bipartite graph. What is a complete bipartite graph? So, a complete bipartite graph means, so we should be able to group the vertices into 2 groups such that, so let us say this is A and this is B, and then whenever I have an edge here, say vertex here, and then whenever I have a vertex y here, then there will be an edge here. In other words, all the pairs with one from A and one from B will form an edge. So, usually we will show it like putting, so say thick, sorry. So, we can show it like selecting, so like this, all the edges are there. So, we can indicate it like this, all the possible edges between A and B are there. This is called a complete bipartite graph. So, notation for this, and suppose there are m vertices in this A side, n vertices in this B side, then we will call it KNM. This is the notation for that. Remember, the complete bipartite graph was Kn with n vertices. Here this KNM, n for the number of vertices here. Oh, sorry. So, let me say KMN, or so as we wish, KMN. So, this is a complete bipartite graph. And from now on, I will introduce some concepts, concepts about graphs. The first one is called a vertex cover. So, what is a vertex cover? The set S of the vertex set of G, S subset of V of G is a vertex cover of G if every edge of G is incident with a vertex in S. A vertex cover of the minimum cardinality is called a minimum vertex cover. So, let us take an example to explain this. So, consider this graph, simple graph. So, a simple graph. Now, I am asking for a collection of vertices such that every edge has one of the endpoints in this set. For instance, let me show an example. So let me take this vertex and this vertex and this vertex. Now, you take any edge, suppose this edge, it is one red endpoint. So, this edge, it is one of the, in fact both the endpoints are red. Here another edge, it is one of the endpoints as red. So, another edge, so one endpoint is red and another edge, one endpoint is red. So, every edge is such that it has at least one endpoint as red. So, then these three vertices, the set of these three vertices, the red vertices is called a vertex cover of this graph. So, interesting way of explaining it is, suppose you consider a museum. So, museum is, say, let me draw, say something like this. So, these are the corridors where the museum articles are displayed. So, museum or art gallery or something like that. So, maybe so here we have to place some sentries such that, for instance, if a guard sits here, a sentry sits here, he can see this corridor, and make sure that the people are not stealing things from the art gallery. So, these three ways he can watch for, but on the other hand, he cannot see what is happening here. So, similarly, if something is, some theft is happening here, he cannot see that. So, he may have to place another person here, so that he can watch here. So, he watches this and this. So, who will watch this one? You may have to place one here. So, if you place one sentry here, one sentry here and one sentry here, they can together watch the entire museum. So, no theft will happen, right. So, here this problem can be modeled as a graph problem, as you can see. So, here this will be converted to a small vertex, and then this will be converted to a vertex, this all the corners will be converted to a vertex. So, I will say I can draw a graph like this based on this, and it will look like this. So, this is the so I have formed a graph from this art gallery. So, where these are the places where we can possibly place the sentries. So, there is no point placing a sentry here, we can only see here. So, if he is here, he can see anyway this. So, these are the corners, and then these are the corridors along which people move and the articles are displayed. Now, the question is the same as asking what is the minimum vertex cover here. Why minimum? Because we want the minimum number of sentries to be placed to minimize the cost. So, see, so here if you place, as we saw, we can place one here. So, this we can say select this vertex. So, as a position for sentry, placing the sentry, and or we can select this one. So, this will so together this one, these two is a covered, this is covered, but now this is not protected. So, if I place one here, then you can cover this thing, but still it will be, this will not be covered. So, therefore, I can place one here, this thing. So, the minimum number of guards we have to place, so that the entire museum will be watched, is the same as the minimum number of vertices that we have to be selected, such that every edge has at least one endpoint in it. So, this is called a minimum vertex cover. So, the vertex cover is just a collection of vertices such that every edge has at least one endpoint in it. Minimum vertex cover is the one which minimizes the cardinality. That means, we want the smallest vertex cover. Now, to get familiar with what is a vertex cover, we can ask the take some examples and see what are the what is the cardinality or the minimum vertex cover in those graphs. For instance, our first graph, the complete graph Kn, what is the cardinality of the minimum vertex cover in a complete graph? So, it is so easy to see that, for instance, if there are 10 vertices and if you just take one vertex, this one vertex cannot cover all the edges, right. So, how many we will need to cover? So, with some thought we can understand that we will have to take. So, okay, if we take n minus 1 vertices from the n vertices, then we can cover all the edges. Cover the edges means, so the all the edges will have at least one endpoint in it. For instance, so let us say this complete graph, this is the K4, the complete graph on 4 vertices. Now, if I take say if I take this one and this one, then you see that all the edges are covered. It is very easy to verify. But now the question is it possible that, so the from this thing what do we get? There exists a vertex cover of cardinality 3, that means say n minus 1 for a complete graph on n vertices. But is it possible that we can cover all the edges of a complete graph on n vertices by less than n minus 1? What if it is possible? Some clever way of selection, but some thought will reveal to us that it is not possible, because suppose we can do that, using just n minus 2. Suppose there is a vertex cover with n minus 2 vertices, then there are 2 vertices, say let us say x and y in the graph, such that it is not in this vertex cover, because we have in the vertex cover we have only n minus 2 vertices. There are 2 more vertices, let x and y be these 2 vertices. So, because it is a complete graph, between x and y we do have an edge, neither x nor y is in the vertex cover we have selected. So, who is covering this edge, right? So, therefore, if we have only n minus 2 vertices in the set we have selected, it cannot be a vertex cover. So, the number of vertices in the vertex cover of a complete graph is at least n minus 1, and its n minus 1 is enough. Therefore, for complete graph the cardinality to the minimum vertex cover is n minus 1. Now, let us consider another example. So, what about a complete graph on complete graph Kmn on so with m vertices on one side, complete bipartite graph, so not complete graph. So that it is like this, for instance, m vertices here, n vertices here. So, it is a bipartite graph, this is an independent set, this is an independent, there is nothing inside it, no edges there. And then, for instance, we can say it looks like this. So, all the edges are there in here, all the edges are there from this to this, right. We have to cover all these edges. So, what is the minimum? So, if you see that, suppose if I take all these vertices, then definitely it will cover all these edges, because every edge has to have at least one endpoint in this side, or if I take all the vertices from this side, that is also enough. So, since we are looking for a minimum vertex cover, so we will take the smaller side if m is less than or equal to n. So, we can go for this thing. This will be this side, for instance, if this is A and this is B, then A will be a vertex cover, but is it minimum? That is the question. So, can we do in with less than m vertices. So, it is not possible, because suppose we can do, and then so if we do with less than m vertices, definitely there is a vertex here, say x, which is not part of the vertex cover, x is not part of the vertex cover. Similarly, there should be a vertex here y, say, which is not part of the because this is more than n is more than m. So, we have taken less than m vertices. So, there should be a y. So, and also because it is a complete bipartite graph, there is an edge between these two, this edge, who is going to cover them. So, the edge between, so x y. So, there should be an edge between them, who is going to cover that edge. So, it is not possible to cover all the edges of this complete bipartite graph K M n with less than m vertices. Next, so what about the cycle on n vertices? So, suppose if we consider the cycle on n vertices, what should be the cardinality of a minimum vertex cover? So, here I have drawn a cycle on 7 vertices. So, let us make it 8. Let us make it 8. So, it cycle on 8 vertices. So, now you can easily see that. So, a vertex cover, so I am marking a vertex cover here. So, 1, 2, 3, 4. This is a vertex cover. 4 vertices is enough to cover all the edges. You take any edge, one of the endpoints is right. Now, the question, so for instance, if this is a cycle on n vertices C n with n even, then it is clear that n by 2 vertices will be enough. You can take alternate one here, then next here, then next here, like that. So, n by 2 will be enough. But then the question is it possible to do with less than n by 2 vertices? So, without much difficulty, we can see that it is not possible, because if you look at each vertex, each red vertex here, it is only covering 2 vertices, because the degree of this graph, degree means the number of edges incident on the vertex is called the degree. Degree of this graph is so degree of this vertex is only 2. So, degree of this vertex is only 2. So, therefore, so each vertex is covering only taking care of only 2 edges. So, together n by 2 vertices can take care of only n edges. So, for instance, if you could do it with n by 2 minus 1, that will take care of only n by 2 minus 2 edges. So, the remaining 2 edges will be left uncovered. So, therefore, n by 2 is a must. Similarly, if you consider, suppose n is an odd number, then you can easily see that you need n by 2 seal, right, because if you have n by 2 say floor also. So, each vertex will cover only 2. So, that will be less than n. That will give introduces this notion of vertex cover. Now, let us consider another parameter which is called, we have already talked about independent set. So, the independent set means if it is a subset of vertices such that if you take the induced subgraph on this set of vertices, then what we do not see any edges in it, it's a without any edges, then it is an independent set. So, given a graph G, we can ask what is the biggest independent set in it, what is the biggest cardinality, the maximum cardinality of any independent set in it. So, that number, the biggest cardinality of an independent set in a graph is called the independence number or stability number of G, and this famous parameter is the notation for this thing is alpha of G. We can we can again consider in our so for getting familiar with this parameter, we can consider these questions. For instance, in a complete graph Kn, what is the cardinality of the biggest independent set? So, of course, there exists an independent set of cardinality 1, because if you just take one vertex, there is no edge in it. But is it possible to have anything more, anything bigger? Suppose I take any two vertices in a complete graph, between these two vertices there is an edge, therefore, it is not possible to have an independent set of cardinality more than 1. Therefore, the independent stability number of Kn is equal to 1. So, now what about say the complete bipartite graph on Km and Si, as we mentioned this one, right. So, when we have this all these edges, m vertices here, n vertices, the biggest independent set. So, it has to be n, right. Here you can see an independent set, n is the bigger number. So, what if it's because it cannot be more than that, because suppose an independent set cannot have a vertex x from here and a y from here, because there is a connection between them, right, an edge between them. So, it is not possible to have one vertex from this side and one vertex from either. We have to take all of these things, either or we have to take all of these things, right. So, the best thing is to take the bigger side. So, therefore, for Kmn it will be right independent, this thing is n, because n is the bigger number. Now, of course, we can like this, we can also ask what is the biggest independent set in a cycle Cn. So, n is even. When n is even, of course, we can take 1, then we can take 2, like that, all the vertices skipping alternate things. So, we will get n by 2. So, when it is odd, so for instance, we can consider this 3 vertex graph, and then here we can see that this is 1. So, then we cannot take this or this. So, 3 by 2 floor is the answer, this one. So, we can take a bit bigger one. So, a 5 vertex graph. So, we can take 1 here, 2 here, that is it, because if you take 3 here, this adjacent to 2, if you take this one, this adjacent to 1. So, this is 5 by 2 floor 2. So, for an odd cycle, it is n by 2 floor. Now, we have studied two parameters now, the vertex cover, minimum cardinality of the vertex cover, and the independent set, the maximum cardinality of the independent set. The next question is there any relation between these two parameters? To see this thing, so we can say that suppose if you remove a maximum vertex cover, any vertex cover from the graph, what will happen? So, if you remove the set of vertices that form a vertex cover from the graph, what will happen? The remaining vertices that you see is going to be an independent set. Why is it so? Because if there is any edge in this the remaining collection of vertices, then this edge will not be covered by anybody, because what we removed was a vertex cover. So, then one of the endpoint of this edge has to be in that. So, if you remove a vertex cover from the graph, what we are left with is an independent set. So, therefore, we can see that if you remove a minimum vertex cover, then what remains? The n minus the cardinality of the minimum vertex cover number of vertices form an independent set. So, that is what we have written here. So, therefore, our maximum independent set cardinality has to be even greater than this. So, alpha is greater than equal to n minus MVC of G. That is what. So, here for instance it is like this. So, suppose this is, I draw a graph like this now. Suppose you can mark some vertices as this is the minimum vertex cover, say let us MVC. So, here we have n minus cardinality of MVC number of vertices. This is going to be an independent set, this is independent set. So, the biggest independent set has to be even bigger than this, possibly even bigger than this. That is why we say alpha of G has to be greater than or equal to n minus MVC. Similarly, what will happen if I remove an independent, suppose this graph, and I mark an independent, suppose this is an independent set. Let us take the biggest independent set maximum, and remove it. So, clearly what remains here is going to be a VC, vertex cover. Why? Because any edge is going to be like this only, it is not possible to have an edge like this. So, any edge is has at least one of its endpoints in this part. So, it is a vertex cover. So, the minimum vertex cover has to be even smaller than this. So, we get cardinality of the minimum vertex cover is less than equal to the number of vertices minus alpha of G. This cardinality is alpha of G, because it is the cardinality of the maximum independent set. So, from the earlier slide we see this can be rearranged to write cardinality of MVC is greater than or equal to n minus alpha of G. Here in the other side we can see that cardinality is less than equal to n minus MVC. So, together what we get is cardinality of MVC of G is equal to n minus alpha of G. So, in other words, what we are trying to tell is, so if you remove a minimum vertex cover, what remains is a maximum independent set. Similarly, if we remove a maximum independent set, what remains is a minimum vertex cover. So, this for cardinality of the minimum vertex cover we can probably denote by say beta of G, because say we are using alpha of G for the independent set, and we can use say for the minimum vertex cover cardinality beta of G. So, then what we get is the cardinality of this and the cardinality of this, the independent set, maximum independent set and minimum vertex cover together is the total number of vertices. Alpha of G plus beta of G is equal to n, where n is the number of vertices. So, in this class, so to summarize, we have introduced some basic terms that are used in graph theory. So, of course, there are many more terms that we have to introduce, but as the lectures go on, we will talk about more and more things. But I would request the listener to also go through some introductory chapter from any of these books I mentioned, so and solve some problems, so that he can think along the class and understand things faster. And also it is very boring to introduce every small definition in the class, so that we can use the 40 lectures available for more serious discussion. And then after that we introduced a few notions like minimum vertex cover. Then we told the minimum vertex cover is the one with the minimum number of vertices in it, and another notion independent set. We talked about the cardinality of the maximum independent set, that is called the stability number. The notation is alpha of G, and then we related these two parameters alpha of G and the cardinality of the minimum vertex cover, we called it beta of G. It's so that when you sum them together we get the total number of vertices. This is because when you remove a vertex cover, what we see is an independent set. Similarly, Therefore, when we remove a minimum vertex cover, what we see is a maximum independent set and vice versa. That is the reason for that. So, this summarizes the lecture today. In the next class, we will look at matchings, and then we will connect the matchings, the notion of matchings with the vertex cover and independent set, etc. through some. That will be the aim of the next class. It would be better if the student can, as I mentioned, go through some of the introductory material in any of these textbooks, so that the next class will be much easier.